afternoon, everyone. I fixed the camera position. Okay. So just to recap the whole story a little bit, we said, okay, it's a good idea to, or a lot of systems can be described in mechanical engineering, aerospace engineering, by ODEs, by differential equation. I've shown you a couple of examples where they actually come up. And we started to classify those systems, right? And we started out with the proportional system. So this was our first class, and we decomposed those basically in pure proportional system, and then we talked about the first order or proportional system with a first order lag, and last time we mainly talked about the proportional system with a second order lag, right? We learned that it can oscillate, it can be aperiodic, so we had this case discrimination there. Okay, so good news is I'm not going to talk about third order, fourth order lag, because we will learn today that every system can be decomposed in PD1 and PD2 systems. So there's no need, we can stop after that. What's left then, guess for the second part of the lecture today, is then integrating and differentiating systems. Remember, these are the three big classes we have: proportional, integrating, differentiating, but a system could be a mix of those three. That's the important stuff here. Okay, so let's take a look at our PD2 system. I will go through it very quick, what we have done last time, just to give everybody a heads up. Okay, so we said that we have this case discrimination where our eigenvalues can be real or they can be complex. If they are real, we actually have a non-oscillatory case. If they turn out to be complex, if we solve the midnight formula, the Mitternachtsformel, we are actually realize they have in the solution our system's going to oscillate, right? Okay, so we went through those two things. I've shown you a PD2 system usually has this S shape, right? This is how you recognize that it's actually not a PD1 system, but something of higher order lagging. We discussed, here we are, then we discussed case number 2 where our system is oscillating, so the eigenvalues get complex, right? So we said, okay, instead of writing our equation with B2, B1, we prefer to use a damping coefficient and the eigenfrequency, right? I've shown you the solution to a step input, and what shows up there is if we just wait long enough, so if we let time go to infinity, we are left with the proportional system, right? So all the eigenmotion here actually vanishes, and what remains is y is equal kp times 1, because the input is 1, right? So the eigenmotion is basically what happens in between, from the start until we have our constant value, right? And here we see, because we are complex, we have complex eigenvalues, we are oscillating. So this is what we call the eigenmotion. Okay, then we started discussing a little bit about this omega and this the eigenfrequency and the damping. I guess most of you know, remember that from technical mechanics, right? So we said, okay, if we have a system and we are just changing the eigenfrequency, we are seeing that actually the thing gets faster, right? So if the eigenfrequency is changed, we simply get a faster response in our system. It does not change the overshoot, meaning the overshoot by how much we oscillate over our finite value. On the other hand, if we change the damping, right, and this is kind of, yeah, what we would expect. If you have a spring mass damper system and you change the damping, you make the damping lower, you will see that the system is oscillating more. If you increase the damping, for example, to 0.9, you see this magenta line here that it's rarely oscillating. So what we figured, okay, besides the eigenfrequency and our damping, it kind of makes sense to talk about the overshoot, right? This guy here, and the settling time. Meaning, what's the settling time? The settling time is how fast our system is responding, and that's where we stopped. Actually, we started with the overshoot. So we said, okay, let's take a sample response like this guy here, and define the overshoot. And the overshoot is just a number in percent, how much we overshoot here compared to our steady state value. If you want to do it mathematically, you can say, okay, take the maximum of my response, which would be this point here, subtract the steady state value, this is this A0 here, and then divide it through this steady state value, right? This A0 here. So this is the short form. Multiply it by per 100 to get percent. If you prefer not having percent, but just a number between 0 and 1, don't multiply it with 100. Okay. A nice thing about this overshoot is that we can use this idea of the overshoot to compute our damping and our eigenfrequency, right? So why do we actually need this? Well, you could say now I have my system, I know the damping, and you know the eigenfrequency. Well, not always, right? If I give you the ODE, or you get it if you're working and you get a model of your system, it's a second order system, then you easily can compute the damping and the eigenfrequency, and we are actually going to do this today. However, if you don't get this ODE, right? Again, remember, these are these two approaches we have. Either we get a model, or we kind of design our model by modeling our process, then we know what D and omega is. We rely on manufacturer data of what the spring looks like, how the damper looks like. Okay, this is the one approach where we immediately have our damping and omega. The other approach is we say, okay, we don't have any data, we just have a system. For example, like this guy here, right? So I don't have any ODE of this one. So what do? Well, you could say, let's do an experiment, right? Now you can think of an experiment, what you can do with this one. So you make an experiment and you figure, oh, okay, it looks like a PT2 system. Now you know the ODE for PT2 system, but you don't know the numerical values. You don't know what the damping is or what the eigenfrequency is. But you can draw this PT2 answer, right? So you have a line which is oscillating somehow. And now you can take that response and measure the overshoot and calculate back to the damping. Why do you need that? Well, the ultimate goal is always to have a description, a mathematical description of your system. Why? Because you ultimately want to design a controller for it, right? So it's, again, this is important. The first, how do we get to this ODE having numerical values? You can either go from modeling it with equations, or you can do an experiment. And if you do the experiment, you need to then calculate your damping and your omega. And this is the approach how we would do it. Okay, so let's assume you did the experiment and you get this blue line, right? You can measure now the overshoot. Just take a ruler. And you can also calculate it, right? And if you take the overshoot of the second guy here, you actually can relate these two overshoots. Well, let's say A2 is an overshoot. It's not really called an overshoot, but let's take this amplitude A2, and then via a logarithmic function, you actually can back compute to your damping. Take that damping and take this time you need from the first to the second peak and calculate your eigenfrequency. So, and this is actually what you're going to do in the second lab exercise, right? Or you did it in the first exercise for a PD1 system. You did an experiment and computed your ODE. You took the answer of your system and computed the numerical values. Remember, you could do it. You can always do it differently. You can say, okay, this is an espresso machine. I have a heating element, and I get a data sheet of the manufacturer having this and this heat coefficient and so on. So you can go ahead and model this guy and plug in all the manufacturer data and still end up with the ODE. So you have basically two ways to get to this ODE with numerical values. And in the second lab exercise, we're going to close a loop. We're going to actually do a controller to our espresso machine that we try to get to the 96 degrees. And this system will be a PD2 system. And then we're going to try to identify this PD2 system. It's basically doing the experiment with a controller in there and trying to identify this loop, this system dynamics there. Okay, this is where we stopped last time. So What we didn't talk about was the settling time, and this settling time is actually pretty important if you do flight control. Why is that? Well, especially if you work with fighter aircrafts, because you want to design a good control system for your aircraft, right? You care about how fast your system is. With the espresso machine, well, you also care about if it takes 1 hour or 5 minutes to heat up your water. But I mean, if it's 5 minutes or 5 minutes 10 seconds, probably not that big difference. But for different applications like race cars or like fighter aircraft, where you try to squeeze out every inch of performance, this here could be important, right? Because you want to have a system which is responding very fast. And this is where the settling time comes into play. Okay, so let's talk about the definition of the settling time. Well, the settling time just says, okay, or is defined by a kind of band, right? Some band. When your answer stays within plus minus 5%, right? Okay, let me try to draw this band, what I mean here. Okay, let's try to do. Okay, this band here is, okay, we are looking at our stationary response plus minus 5%, right? So here for this step response, okay, there was not a straight line here. Here our final value is 1, right? Oops, sorry. This one. So here our final value is 1. Okay, plus minus 5% is 1.05 and 0.95. Okay, now we define the settling time when our output stays within these limits, right? So we want to stay in between in there, and this defines our settling time. Okay, so now let's take a look. Okay, here we are in there, but we're leaving it again. So that's not the settling time. So here it looks good. We're back in, but we're leaving again. Okay, not good. Okay, here we're there, and now we're leaving it a bit, and we're coming back in. So we left here, right? Left plus 5% basically. Okay, we have some lag in there. Okay, and this now is the time where our answer decides to stay within plus minus 5%. Okay, and now we define this as settling time, right? This settling time actually also works for a PT1 system, right? So this is not only for a PT2 system, the definition always holds. So if we do a PT1 system, we have learned that, okay, our system responds like this. However, for a PT1 system, it never will go above plus, or actually plus 5%, right? Because it cannot oscillate. So for a PT1 system, only the 95% line is important. And here you know that minus 5, let's do it uniformly. You know that we are always reaching this 95% at 3 times our time constant. So the settling time for a PT2 system is pretty simple, right? It's just 3 times our time constant, because we know after 3 times our time constant, we are reaching 95%. For PT2 system, it's not so straightforward anymore, because it can oscillate over and under, right? So it's not that easy to compute. Okay, so actually it is also easy to compute, to be honest, but it's not. It's a little bit more to understand, I guess. So actually, yes. Let's get rid of this so I'm not interfering. Okay, so if you look at the time response on slide 24 or 21, so let's go back to 21 to get what I mean. So this is the time response to a step, right? You see that there is this exponential function plus multiplied with the sine wave. And what does it mean? This exponential function, what happens is y of t is some exponential function, which is hopefully, if it's stable, it's looking like this. It's multiplied, let's do this, multiplied by a sine wave, right? Okay, so the output is simply a decaying sine wave. So this exponential function has something to do with, let's do real t, has something to do with our reaction time, right? Because the sign does not change over time. Okay, and the matter of fact is, if you look at this exponential function, which has our real part of the eigenvalues there, right, is equal to our damping times our eigenfrequency. So this exponential function is nothing but d times omega 0. So far, so good. And now we can relate that back actually to the PD1 behavior. So if, and this only holds if your damping is lower than square root of 2 over 2. This guy is pretty important here. It's basically 0.7. You will see that number a lot in controls. So if our damping is smaller than 1, we can actually calculate our settling time by just taking this exponent here, as we would do with the PD1 system. Remember, in the PD1 system, what we do have here is e to the power of t over t. So this is the time constant of the PD1. So we simply take 3 times this guy here, right? Okay, in case our damping is smaller than 0.71, we can just say we are taking 3 times our exponent of the exponential function, which is d times omega, like this t, right? We are taking t of 95% is equal 3 times t for the PD1. For the PD2, it's the same thing. We're just taking that exponent, so the real part of our eigenvalues, which happens to be equal to d times omega 0, and multiply the inverse by 3. Done. Okay? Okay, so you might now say, what happens if our damping is not below 0.7? Well, if it is somewhere between 1 or like 1.2, it gets complicated. It's better than to do a simulation and check. However, if D gets really big, let's think about that for a moment. What happens if we get a very huge damping, like D equal 10? That means our system is overly damped. And the matter of fact is, if our system is damped a lot, we are actually having a PD2 system which has real eigenvalues. And remember, real eigenvalues mean that our PD2 system is nothing but 2 PD1 systems, right? Remember last time we said if our system is non-oscillating, the PD2 system is nothing but 2 PD1 system, because a PD1 system is not oscillating, so we can decompose it. And now here's the trick. The bigger the damping is, the more different are the time constants of this PD1 system. So let's say you have a damping of 100, you might have a time constant of your first PD1 system of 1, the other one's going to be 0.001. So with increased damping, the time constants deviate from each other. What does that mean? If you have 2 PD1 systems and one time constant is pretty fast, the other one is pretty slow, the slow one will dominate your response. So you basically don't care about the fast one. And this is why, if you have a huge damping, you can just say, okay, my settling time is 3 times the time constant of your dominating PD1 system. I guess this takes a little bit of thoughts, but I try to explain it illustratively, but this is what we hear. For very large dampings, one eigenmotion dominates the response, right? So only one of the 2 PD1 systems are important. And it follows then the PD1 case where we just take the real part of this eigenvalue here, of the dominating eigenvalue. Okay, let me try to kind of draw what I mean. That might help a little bit. Okay, so we have one system which is pretty slow. So first PD1. second PT1 is pretty fast, right? And pretty fast, I mean the time constant is really low. So it's jumping nearly up there. So the reaction time is really fast. Okay, what you get for the PT2 system, if you basically multiply those together, is nothing but this guy dominates your answer, right? And we need to start like this. I'm accelerating a little bit, right? We need to start flat and then go up. No, not this way, this way. Okay, so this guy here dominates your answer because this one is so fast that you barely see it. So that means that the overall system mainly behaves like this one, and this is why just take this guy and plug it in to compute the sampling time. The settling time, something. Okay, hope that helps. So where are we? For our PT2 system now we have damping and we have the eigenfrequency, but we also, we said, okay, this is not really enough, right? Or what, not really enough, it's kind of more illustrative, not talking about the frequency and the damping, but about the overshoot and the settling time. Because if I give you, okay, the system has an eigenfrequency of 100, you could say, that's pretty fast, but it's still a frequency, right? If I say, okay, it has a settling time of 0.3 seconds, you know immediately, it just needs nearly a third of a second to reach 95%. So this is for us as engineers, it's easier to understand the settling time than the eigenfrequency. And the damping relates to the overshoot, right? Say, okay, 20% overshoot. You know, if I put in a step input in my aircraft, it overshoots 20%. Kind of, I can relate that to something I can actually feel, right? If you drive your car and I would say, okay, your car overshoots 20%, you would not be really happy. If I tell you, okay, your car has a damping coefficient of 0.3, you say, so what? Okay. So that's why we're moving from eigenfrequency and damping to two parameters we are kind of can feel better. Okay, so why we are doing all of this actually? Well, this is actually relating now back to our first lecture where we said, why do we actually doing control? The idea of control is that we actually can modify our system. So that means that by an artificial system, we can change the eigenfrequency and the damping of our system. So, for example, I give you an aircraft, this one, and the aerodynamics are nicely designed and so on, and you do an analysis and you figure out, okay, if the pilot gives a stick input, the aircraft is 25% overshooting. Is this good or not? Probably not. It's too much. So what do? You want to redesign the whole aircraft? Probably not a good idea because at this stage the wings are or get already built. Okay, so you could say, no problem for me. I can actually take a control system and modify the dynamics of this guy here. I can reduce the overshoot because I only need to increase the damping, right? Okay, so this is the idea why we are doing all of this. Ultimately, we want to take a controller and change the system. Don't get me wrong here. Control engineering is not about fixing things someone else screwed up, right? So be careful here, because usually when you think of a fighter aircraft, it's going to be unstable. That means if you have a fighter, so this is not a fighter, right? But if you have a fighter and the pilot pulls the stick, it will go like this. So you need to stabilize it. You need to increase the damping with your controller. So would you say now, okay, the aerodynamics guys screwed up the design of the aircraft? No, they designed the aircraft unstable because it has some advantages. When operating it can fly faster. But this performance increase comes with the drawback that you need the controller to stabilize it, right? And the same goes for the aircraft. For a civil aircraft. This aircraft will, when you build it this way, will fly in each altitude differently. Why? Well, just think of it. If you increase the altitude, you change the dynamics of the aircraft. I'm not getting the word in. Dichte. Okay, so anyway, the dynamics of the aircraft change. So because of the change in the dynamic pressure, this change results in that your damping changes, right? So you will have these damping coefficients D different in every altitude. And this might be a problem for the pilot because technically in every altitude he has to fly the aircraft differently. And this is not good. It's like when you drive your car, you know, today it's a little bit icy probably. It will behave differently when there's no ice. But ultimately, okay, you can think of if there's ice, I will drive carefully. But for the pilot, he cannot say, okay, I don't want to fly at 30,000 feet. I want to, because I don't like the behavior there, right? So this is probably not a good idea. You can say, I don't want to drive these icy conditions. So that's why we are designing controllers that the aircraft behaves in every altitude the same way. For example, it has the same damping or the same overshoot in every altitude. So this is the idea. This is why we are actually doing all of this. The question now is, what damping should I put in, right? And this is what we're going to do next. What are good dampings you can look at? Obviously, it depends on your design criteria. Do I have an espresso machine where I want to go very fast? Do I have an espresso machine where I actually want to avoid overshoot? So this is on you to decide. For aircraft, you usually say, okay, fast is usually a good idea. For espresso machine, fast might not be the ultimate goal, right? Why? Actually give you a nice example in a minute. Okay, so let's talk about the settling time. So if we look at different settling times and plot it over the damping coefficient, right? So what you should have learned by now is if I have a damping coefficient lower than 1, we are actually oscillating. That means our eigenvalues of the PT2 system will be complex. Sorry, C. Here, our lambdas will be real. Okay? So, okay, let's talk about this oscillating part first because I think this is the more important. When the damping is rather low, and please note we are a logarithmic scale, so this is 0.01, this is 0.1, and this is 1. This is 10, and this is 100. Why we are doing this? Well, because this area here between 0 and 1 is more interesting than this, so we are basically can compress this area, which is basically going from 1 to 100. Yeah. So if we have really low damping, we are here, right? Let's just get rid of this and change the color. Why do we have a big settling time when we have low damping? Well, let's take a look. If we have a low damping, we said, okay, this guy needs forever to go down, right? Probably this. It takes forever to. So when we stay until the moment we stay in this in this plus minus 5%, it takes some time. Okay, so now increase the damping. We obviously go down here, right? For example, we're taking this 0.1. We might already be a little bit faster. Here, it could look like this, right? So it's getting faster. Okay. Increased damping, we are reducing our settling time. This is actually what we figured a couple of slides before, right? Here. Increase the damping, so moving from the orange to the magenta ones, we get actually a lower settling time, right? Okay, but why the heck is this moving up again here, right? So why is this happening? Well, now remember what happens if we have a damping of equal 1. As soon as we have a damping of equal 1, we have two real eigenvalues. That's what we call overly damped, aperiodically damped. Okay, as soon as we are here, we are starting to have this response. No oscillations anymore, right? And the further we are moving away, the longer it takes, right? So, right? So, because the damping increased, just think of a spring and a damper. If you have very low damping, it oscillates forever, right? It will take time to reach this plus minus 5%. Now increase the damper very hard and move your spring down, and it will go back very slowly. Again, it takes a lot of time to reach this 95% here. The optimum is somewhere in between, right? We're still oscillating, but not too much. And the matter of fact is that the optimum is at 0.71. And this is again equal square root of 2 over 2. So why are these looking like these stairs? Well, this is a numeric problem coming from MATLAB, right? So you can think of this as straight also. However, the minimum is at 0.71. So what does that mean now for your design of your system? Well, this says when you have if you say my system is behaving like a second order system, a proportional system with a second order lag, and I want to make the settling time as fast as possible, what should I do? Well, then you need to take a damping coefficient of 0.71, right? Now, you could argue, okay, I can increase my frequency as well, right? Obviously, if you increase your frequency, then it also will get faster. This plot is for normalized frequency, meaning that we took the frequency out of the equations, because the frequency is usually like the bigger constraint here, right? Say, I want to design my aircraft and it should have like a frequency of 4. Okay, I set it to 4. It gets me in the interesting frequency in the time response range. But what do I do with my damping now? To make sure that you have the fastest time response for a given frequency, you need to set it to 0.7. Okay. We are done with the aircraft. Now think of the espresso machine. Okay, so I want to have my espresso machine as fast as possible. So I set the damping to 0.7. Okay, you can do that. Remember now, we have two parameters. We have not only the sampling time, but we also have the overshoot. And we figured, okay, a damping of 0.7 might not have zero overshoot. That's what we want to go look on the other side. So if you now take your damping coefficients, D, and plot the overshoot with it, right, in percent. So this guy here is actually in percent. This way around. No, the other way. Okay, you know what I mean. So this is in percent. Okay. You realize when I have D equals 0, my overshoot is quite a lot. And actually it goes to 100%. If I increase my damping, it goes to 0. Why do I not plot damping over larger than 1? Well, because damping larger than 1 always have 0% overshoot. Remember, if I have a damping larger than 1, I basically have two PD1 system, and a PT1 system always has no overshoot, right? So everything, all the dampings larger than 1 are not interesting for the overshoot. The key element here, what you need to look at, is the following. We say, okay, the optimal damping is 0.71. So if I take a look at the damping 0.71, I figure it comes with a 4.3% overshoot, right? And this is what I mean with design constraints. If you design an aircraft and you say it should be as fast as possible for a given eigenfrequency, you need to set the damping to 0.7. But you need to be aware of that it comes with the price tag, so to say, with the Steuer, that you need to pay for that fast response with a 4% overshoot. So is this a problem? I don't know. Depends on the design. If you design an aircraft, you say, okay, 4% overshoot means if the pilot puts in a stick input, it shoots over and then goes back. Could be acceptable. And actually, for aircraft designs, this price is, you're willing to pay this price of this 4%. When would you not be willing to pay the price? Let's say you want to build an espresso machine and you want to achieve a temperature of 96 degrees. And you want to make it fast as possible. You say, okay, I set the damping to 0.7. Okay, now we're setting 0.7 and say, okay, 96 degrees times 1.043. Well, you will get an overshoot of 4%. You will get 100 degrees water temperature. So, are you willing to pay that price now? That's the question, right? Because what happens, your water will start to boil in your espresso machine. So that's not good. So you need to build a pressure tank around, so to increase the boiling temperature. Are you willing to pay the price? Depends on the customer, I guess. I don't think you would pay that price. So this is now where the engineering comes into play, right? You have a lot of design options here. For an aircraft, could be good to have it as fast as possible, but that's not always the case, right? To be honest, you need to select a damping when you design your system and then go back and relate it to, for example, the overshoot, right? So usually in controls you will hear, always set the damping to 0.7 because it gives you the best settling time and only 4% overshoot. But again, I want you to have some hands-on experience. It really depends on your design problem, and it's differently if you design an espresso machine, a car, or an aircraft. Always think back of these connections there. Okay. So long talk about one slide, but I think that's important. Well, to be honest, in our examples here, I will give you the damping where you should set your system. But you will see in lab exercise number 2 that if you set the damping too low, it will overshoot to a certain value. And is this realistic? If you want to heat up your water to 120 degrees, well, at some point you need to build this whole thing, right? And it's probably not a good idea to heat it up. So for some problems it can work, for some not, and this is the task of an engineer to decide. Okay, so don't be scared, the next slide is going to get faster, but this I think is an important one. Okay, so these next slides are mainly a little bit of an aside here. Actually, yes. I tried to explain to you that this form here is quite useful for oscillatory systems, right? Because we have the eigenfrequency and we have the damping. However, you obviously can bring every PT2 system, every proportional system of second order in this form. It does not matter if it oscillates or not. But you need to be aware of, if it's not oscillating, your damping will be larger than 1. And this is actually pretty nice. because at the end of the day, you will get this equation with numerical values. And when we are done in a couple of slides, we're actually going to do an example of that. So you just compute the damping coefficient and you immediately know if it oscillates or not, right? Because if D is bigger than 1, it's not oscillating, meaning that it will have real eigenvalues. If it's lower than 1, between 0 and 1, it will oscillate, and actually between -1 and 1, it will oscillate, and it will have eigenvalues which are complex. Okay. As I said, if the higher the damping gets, the slower the answer gets. And the higher the damping gets, the more is it actually going to be dominated by only one of the two PT1 systems, right? Okay. So obviously, I always said, okay, it's if the damping is larger than 1, it's going to be overly damped. It's not going to oscillate. Our eigenvalue is going to be real. If it's below 1, it's actually going to oscillate. Our eigenvalues are going to be complex. I actually never talked about what happens if this damping gets negative. So, and the matter of fact is, if the damping gets negative, you just need to take a look at your time response, right? And this is now the step response, right? The only thing you need to care about if D gets negative is that this guy gets positive, right? So if D is negative, you will have something, well, something times T here, which is positive, meaning that your exponential function will go to infinity. And this is what we call an unstable system, right? If you look now at the time response, the red one is the time response, it will go to infinity. The black one here is only the exponential function. Right, this guy here. So your answer now is dominated by this exponential function going to infinity. The answer still looks like you have the exponential function times your sine wave, right? But now, as the exponential function goes to infinity, this guy here dominates your answer, right? Remember, if the system is stable, if D is positive, this oscillation somehow vanishes if we just wait long enough. So the eigenmotion goes away and our system response is dominated by our input. If the system is unstable, and this is actually indicated by negative D, our system will be dominated by the eigenmotion. Okay, I know this is quite abstract. Again, remember this example. This is a stable system. If I now give an input, an impulse, the eigenmotion vanishes. It's getting back where we were. The impulse influence vanished. It has gone away. If I have a system, actually this guy has positive damping, right? Why is it damped? Because of the air resistance in here. This guy here also has air resistance. However, it's unstable because of how the forces act, right? If I do this, it goes down. Although there's no input anymore, it's not going to go back to its equilibrium point, right? It's dominated by its eigenmotion. It does not matter what the input is, it will always go away. Okay. This, again, we're going to talk about instability a little bit more, but I like to give you a glimpse of it already here. For PT2 system, when your damping is negative, your system is not stable, right? Because the exponent in the exponential function gets positive and it just goes away. Okay, so the next slide is actually pretty important because it relates all these PT2 systems in one slide. So the next one, actually, please really read this one carefully and take some more time at home to look over. So it relates basically our damping to our motion and to our eigenvalues, to this lambda 1 and 2, right? So remember this here, what we call lambda 1, lambda 2. So if the damping is larger than 1, okay, I'm trying to draw it in there. We know we are overly damped, meaning that our system would look like this with no oscillations. That's what we call aperiodically damped, because aperiodic, it's not oscillating. Our our eigenvalues are real and negative. So could be -1, lambda 2 could be -2, but they need to be negative. Why negative? Negative is important because our exponential function then gets to 0. Okay, d equal 1. This is actually a special case, and it looks kind of like this. In this case, it's basically the boundary between oscillating and non-oscillating, and it happens to be that lambda 1 is equal to lambda 2, and they are both negative, right? Okay, now the green one is the interesting case where we said, okay, the damping is actually between 0 and 1, and we have some oscillation there. It's a damped oscillation, so it's vanishing over time, and our lambdas, our eigenvalues, are complex, but they have a negative real part. For example, like this. Again, negative real part. The real part is always the important one because the real part shows up in the exponent of the exponential function. Okay. In case you have d equals 0, you actually have an undamped oscillation. This is the so-called resonance, right? Where it does not vanish. Why is what happens with d equal 1? Let's do here. Well, in this case, we have something to the e to the power of 0, and this guy is 1. So in our time response, this guy here becomes equal 1, and only the maintaining sine wave is the only thing what's left, right? This is the case when d is equal 0. Okay, now we said if d is negative, but between 0 and -1. In this case, actually, okay, I forgot here. In this case, we have eigenvalues which are only complex. So they don't have a real, part, right? So the real part is 0. Okay, I'm running out of space now. Let's get rid of this. So if the damping is between 0 and -1, we are oscillating, but we are unstable. In this case, this is the example from below, we are actually oscillating to infinity. Our eigenvalues would still be complex, but they would have an positive real part. So let's say plus -1. So the real part is positive here. Okay, d -1 is again like a special case. The answer for both of these two will kind of look like this, right? Here we have positive, but they are real, but they are identical again. So lambda 1 is equal to could be 1. Here they are not equal. Lambda 1 is 1 and lambda 2 is 5, for example. Okay, it's going to infinity. There's a special case actually when all of these are some positive omegas. We actually have this special case when omega squared is lower than 0. So omega gets complex. In this case, you actually have a positive real eigenvalue and a negative eigenvalue which is real and a positive one, right? In this case, your answer will also be looking like this. It will also be going to infinity. Why? Because this guy here, well, look at the responses, right? This guy gives you an eigenmotion which vanishes, but this guy goes to infinity. Multiply this together, will definitely look like this, right? So this guy does not contribute much to the response. Okay. What you should take away from all of this is that the roots of this or the eigenvalues itself, right, are the important stuff here. Remember, when we talked about solving ODEs, we said, okay, we have different approaches to solve ODEs. If we have a second order system, we take this way where we actually not solve the ODE, we only solve the Mitternachtsformula for the second order system and compute the roots of the characteristic equations, which are called eigenvalues. The matter of fact is that we only care about these roots in control anymore because we know our system response will be some exponential function and it might oscillate or not. And all of this depends only on this solving the Mitternachtsformel. The midnight formula, right? This is everything you need to know to understand how your system reacts, right? So this should be a takeaway here. Okay, a lot of talking, actually 10, 11:30, right? Okay, just, no, 1:15, so 30 minutes left. Sorry, I'm confused. Okay, now let's go and do a little bit of practice on this PD2 and PD1 system. I'm going to go into MATLAB first and show you a couple of things. And you can download these MATLAB files and play around. I hope it helps you to understand the things a little bit better. And then we're going to do 2 calculations, just that you finally have some numerical values there. Okay, let's switch over. Okay, so let's go back to PD1 first, right? We said a PD1 system has these 2 parameters. It has a time constant and it has this proportional gain, right? And now we want to vary these 2 guys and simulate the system responses. So remember, first, PD1 system is a system with a first order lag. So the PD1 system can actually be a stable one, as we said, can be related to the thought of moving from one equilibrium to another one, like the car, right? An equilibrium would be you have a fixed pedal position, you're driving 100 kilometers per hour. This system is in equilibrium, you're driving constant speed. Now we are moving to another equilibrium. Could be you're moving from 100k to 150. You press your gas pedal, it takes some time, you reach the 150. So this is a lagged response. Oh my God, it's snowing. It's getting dark. It's a lagged response going from one equilibrium to another, right? Okay, let's try this in MATLAB. Hopefully it works. Okay, here it is. So you can download these files if you want and play around. So please, okay, we define our time constant and we define this Kp here. Actually, you could write it in small letters. This is the old version of it. Okay. This is how you define it in MATLAB. We will learn, this is actually already what we're going to learn next week when we move into the Laplace domain. Please, at this point, it's important that this is your PD1 system, and then we're going to do a simulation. Okay, we've learned, okay, Kp equal 1 means that if I do a step response, right, MATLAB actually can, in MATLAB you can do step responses pretty easily because there's a dedicated function for it, which is just called step, and then you call the system. That means if I do the simulation, it should go to 1, okay, because the step is a unit step, the input is equal 1. Okay, now you could say, what happens if my Kp is just 0.7? Well, it will go to 0.7, right? So you simulate, press F5. Unfortunately, the whole thing is a little bit slow when YouTube is running. Okay, Now we're going to 0.7. Okay, so the time constant here is 1 second, meaning that we reach 63% of our answer actually after this time. Okay, to visualize this 63%, I'm moving that to 100, right? So after this time constant of 1 second, we roughly have 63% here. Taking the time constant 3 times, we are 95. So this guy here is about 95 at 3 seconds. No, it's not about, it's exactly. Okay, so now you could say, what happens if I make the system slower? Well, this should now get slower, right? See, we are taking more time because this time we are needing 3 seconds to reach 63%. Okay, now let's take 5 seconds because then we have a cut with our line here. Okay, 63, exactly 5 seconds, right? So this is the step response. I told you step responses are the go-to guys, so to say, if we want to do simulations. But in MATLAB, you can also do different responses. The other important one is the impulse response. So we don't give a constant input. We just want to push it slowly, right? Think of the car example. A step input would, you go with the gas pedal from here to here constantly. An impulse would be, you go just do like this, pretty fast, an impulse. Okay, there's actually also a dedicated function to simulate this input. It's called impulse, pretty straightforward. Okay, so the impulse function for our system now looks like this. Interestingly, it's the PT1 system has an immediate answer to that impulse. Okay, the interpretation of the impulse is basically an initial value problem, right? That means you give it an initial value and see what happens. Okay, that's the impulse response. Okay, what you could try at home is to create an unstable PT1 system, taking that MATLAB file. What you need to do is change one of the 2 parameters here that your system gets unstable, gets to infinite. What parameters? That's your decision to take. Well, think of what stability defines. Stability is defined by the eigenmotion. It has nothing to do with the input, right? So it must be the left-hand side of your equation. There's only one parameter there. Okay, you can play around with this PT1 system, so hopefully you get some more insight. Okay, let's go back to our presentation. The second example is a spring mass damper system, and this should be an example for a PT2 system, right? Again, you can also look at that vertically. I think in an older version of the script, I flipped that 90 degrees around. It actually doesn't matter. I think this way it's a little bit easier to understand because we can get rid of the gravity vector. Yeah. Okay, if you build the ODE, you will see that, okay, I have an input force and I have a damping and I have the spring constant and have a mass. Please, really here, what's important is this damping we have in mechanics is not equal to the damping we have in controls. So, or system dynamics, right? You might have heard it in TM3 somewhere, in Technical Mechanics 3, where you also talk about the damping coefficient. But here, this guy is really the damping coefficient of your hardware, what comes with the damper. This damping then is kind of a unitless damping coefficient, right? So please note the difference there. But I will show you that in the script immediately. Okay. So, okay, here is the MATLAB script for our spring mass damper system. We know You have it in German and in English. What do you prefer? We have this equation here. Actually, just taking a look. Okay, I normalized it in here. Okay, if you divide this guy by C, it will have the same look as in the lecture. Okay, now what we are defining and what you're getting by the manufacturer, right, when you build this thing is probably the mass, or you decide for the mass. You get a spring constant and you get a damping coefficient. Okay, but now when we talk about the damping coefficient, what we talked in a lecture, it's basically made up of, you need to compare the coefficients here, right? This is the mechanical system here on the left, and this is the system what we have in controls, what we defined, or not in controls, more like in system dynamics, right? So if you want to compare the coefficients, you will get your damping coefficient in here, this big D, right? And obviously this damping coefficient depends on the damper, on the hardware part, but it also depends on the square root of the ratio of your spring over your mass. The eigenfrequency mainly depends on the spring and the mass and so on, right? Okay. So I'm computing all of this. I'm computing the eigenvalues with that, and okay. So okay, let's start from here. I have a mass of 1. I have set this C to 1 and this D to 1. If you compute the eigenfrequency, it turns out to be 1. The damping turns out to be 0.5. Okay, this damping coefficient. 0.5, now you immediately know it's going to oscillate because the damping is between 0 and 1. It needs to oscillate. Our eigenvalues need to be complex. That's what we can draw from this first computation here. We're going to look at that. Okay. Okay, this is the midnight formula, right? If we solve that by hand, or not by hand, program it by hand and let MATLAB solve it, we actually get our lambdas, minus 0.5 plus some complex part. So it is complex. We have verified this result. You can skip all of this and just take the system and call it damp. You get everything by MATLAB immediately. You get the poles. Why they are called poles and not eigenvalues, we will learn in the frequency domain. Okay, 0.5 plus 0.8 minus 0.8i, right? The damping is 0.1, the frequency is 1, and actually the time constant, they don't make much sense if the system is oscillating. Okay, so everything's provided immediately. Okay, but now let's take a look at the step response. Okay, 0.5 gives you some overshoot. In this case, I think it's about 18%, and this is the answer, right? The impulse response, okay, looks like this. A proportional system always goes to 0 for an impulse because it's proportional. Why is that? Because a proportional system transports the input to the output proportionally. Proportionally means you take the input, multiply it with the output. And it always, in a proportional system, as long as it's stable, always goes to 0 for an impulse input if you just wait long enough. Why is that? Well, the input is 0. Proportional transfer means 0 times the constant is obviously 0 here. Okay, so what you can do now is here, you can play with the parameters, right? For example, you can increase the damping. Okay, let's do this. Press F5. And now we get a damping coefficient of 5. We immediately know our eigenvalues gonna get real. I actually can go back and check on that here. D equals 5 means we're in this range here. We need here in this first line, we need negative real eigenvalues. Okay, let's check. Okay, minus 0.1, minus 9.9. Okay, they are both real, they are both negative. That's correct. Actually, you can check here. That's why I actually put it in here. But we are getting actually pretty slow. Okay, so what you see here, and that's what you will figure also in the lab exercise. Here we did not simulate long enough that it gets constant again, right? So we can increase here our plotting time a little bit. Still not enough. Okay, let's go to 80 seconds. Ultimately, it should go constant here. Okay, so we changed the damping. Now let's change the spring. Let's do the spring, put the spring coefficient down. You can play around here, right? Now we got a damping of 1.5. Well, it still will not oscillate, but it will be faster. Compared to the one before, it's faster. So now let's go negative damping. Why not? -2. Negative damping here means we will have a negative damping coefficient. It's actually -1 now. Okay, we know it's going to be unstable. You see, it goes to infinity. We are already, after 80 seconds, at the value of 4 times 10 to the power of 36. So definitely unstable. Okay. So please use that file if you get some insight and to get some understanding of a PT2 system, because really this PT2 system is of crucial importance because we are actually referring to that pretty often. Okay, that's where we are. Before we actually start the move away from the proportional system to the integrating and differentiating systems, we're going to do some more calculations. Well, this was not calculations. Were not calculations. We let MATLAB do the job. Now what we want to do is we're going to do some paperwork, right? To see a couple of calculations on paper. Okay, and therefore I'm going to move over to OneNote. You can grab a piece of paper or write it digitally or just enjoy the show. But this time I would like you to work a little bit in the chat. We will just try to see how it works. Okay. Okay. Proportional system mit no width, second order lag. Okay, I'm doing a short summary, so we have all the formulas here. We said, okay, these guys somehow look like this. We have the second derivative of our output, and it's proportional. What does this proportional mean? Well, it means that on the left-hand side, our input acts only proportional, right? So this is why this system is proportional. The left-hand side, it's a second order lag because we have the second derivative. Okay, we said, okay, it also makes sense to transfer because B1 and B2 don't tell us that much. It makes sense to write these guys with a damping coefficient and the eigenfrequency. It's a small k, right? Okay. So we said, okay, omega 0 is our eigenfrequency, and D is our damping coefficients. Actually, I will most likely say is most likely to say that I will refer to damping and not damping coefficients because it's just shorter. Okay, before I continue, I have a question in the chat. I need to translate on the fly. So the question is if you just need to read the graphs and transfer it back to the system, or if you need to solve ODEs. So you will never actually solve an ODE in the time domain, but as we are going to do now with this ODE, you should realize what the eigenvalues are, what the eigenfrequency is, and what the damping is, right? So you kind of start solving the ODE, right, for a second order system. Because when you compute the eigenvalues, you already started solving the ODE. But this is all what we need. We're only going to compute the eigenvalues because when we have the eigenvalues, we already know that our system responses like with these exponential functions. And all of what comes after is not really important. So no, you don't need to solve the ODE for a given input, but you need to be able to compute the eigenvalues and the damping and the eigenfrequency out of a system. And this is what we're going to do now. I hope that helps. Or the other thing is what we're going to do is I will give you time responses, and you should be able to judge what system it is and compute some parameters of that plot. Also, I give you the time response, a line, and you should be able to compute the eigenfrequencies of this. So this is a kind of other approach coming from the experiment and computing the ODE. Or I give you the ODE and you need to understand, okay, what's the characteristic now of the ODE? What's showing up in the solutions? We now know that what shows up in the solutions are the eigenvalues, the damping, and so on. And this is what we're going to compute. You need to be able to extract this. I hope that kind of answers the question. Okay, so this is our system now. And now I'm actually coming back to that question. If you want to know y of t for a given u of t, right? So you want to know your output depending on what the input is. You need to solve the ODE, right? The DGL. But most importantly are the eigenvalues. Lambda 1 and lambda 2. So if you start solving the ODE, you will solve for the homogeneous solution. You will compute these eigenvalues here, right? And then these eigenvalues are going to show up in your exponential functions. But we are done when we have these eigenvalues because we can already characterize the system. Is it stable or not? Is it oscillating or not? How fast it is? So what we are basically doing, right? In mathematics, you have learned, okay, you have the ODE, you need to solve it for y of t. We are basically only extracting the information from the ODE, like the eigenvalues, like the damping, like the eigenfrequency, because we know if we have those characteristics, we already know how the answer is going to look like, right? So we are not going to solve all of this. We are just looking at these parameters, and this gives us enough information about the behavior of the system. Okay. So why is this the case? Because they show up in the exponents of the exponential functions. So, and here's a clue, right? We know that every linear ODE of second order will have these exponential functions in the solutions. So we don't need to compute it because it's always going to be there. We are just interested what's in the exponent of that functions. And this we can simply extract by solving the Midnight's formula. Okay. So, but now let me come to the example. 10 more minutes. Okay. So let's say you were given an ODE and it looks like this. So this could be the case when you say, okay, I'm interested now how my spring mass damper system is modeled, and now it looks like this, right? So, but what do we want to know now is we want to know now omega 0, our damping coefficients, our Kp, and the eigenvalues. So instead of solving this ODE on paper, which will take forever, not forever, but some time, we extracting these parameters, and with that knowledge, we already know everything there is to know, right? Is it damped? Is it overshooting? Is it fast? Is it slow? Is it stable? Is it unstable? And that's it, right? We don't care about a specific input because we know if we have the overshoot, if we have the settling time and so on, we can already visualize how the system is going to responsive to a step. And as I said last time, we stick to the steps, we stick to the impulses at this point. Okay, now here's the job for you. Try to compute Kp here. Well, if you're fast, you can go along with omega 0 and d and shoot them into the chat and give it a try. Okay, what you need to do simply is you need to compare the coefficients, right, between this guy. If you get to 20, that's already pretty good. Why? Because we have a 3 here, but in this case we have a 1 here, right? So we need to divide this equation over 3 first, and we get 0.25 times t plus 0.5 of t plus y of t is 20. So please always remember that you need a 1 here. If you take, there's a different version of this where there's the 1 at this place, right? Then you need to make sure the 1 is here. Okay, now we can actually compare the coefficients. Well, Kp now is equal 20, right? Because this is just Kp times u of t. So this guy is equal 20. What we have here is 2d over omega 0. And what we have here is 1 over omega 0 squared. So if I invert this, omega 0 turns out to be 2. And now I can compute d. So actually what d gets is 0.5, so 0.5, right? It's basically 2d over 2 is equal 0.5. Cancel, d is equal 0.5. Okay, so this is really of crucial importance. We will actually going to do this quite often, and we are always also going to do it the other way around. Okay, now let's compute the eigenvalues. So we already know here d is smaller than 0, right? Well, let's do it correct, fully correct. d is larger than 0, but smaller than 1, not smaller than 0. So the eigenvalues 1 and 2 need to be complex. Okay? Okay, so now let's go for the midnight formula, lambda 1 and 2. And now you can take any form, what you prefer here. I'm just take the first one, right? So it's minus 0.5 plus minus square root of 0.5 squared, which is nothing but 0.25 minus 4 times a 25 and c is equal 1 over 2 times 0.25. 2 times 0.25, which is 0.5. Okay, if you solve that, it's basically this guy here is 0.5, right? So what we have is minus 0.5 over 0.5, which is nothing but minus 1. And then we have plus minus. And this guy, the square root, is definitely going to be negative. So what we have here is minus 0.75, and if you bring 0.5 under the square root, you are left with 0.25. So what we have is plus minus square root of minus 3, right? Which is equal minus plus minus square root 3 times I. And you should see that they are complex, right? Again, that means the system will oscillate. Okay, 3 minutes left. Yeah, why is it oscillating again? Just you should notice now, again, this relates back. Why is it oscillating? It oscillating. Well, our y of t, right? If you solve the ODE, what we not do, because we can just look it up, has something in the solution that there is e to the power of lambda t, and if there is lambda t and e gets complex, so if we insert this plus minus square root of 3i, we know after Euler this can be decomposed in an exponential function with a real exponent and some cosine or sine function, right? So this is really basic maths, what you have learned. Again, this is the justification why this guy here is oscillating. Okay, one last example here, and this is more like, yeah, and to show you how would you solve if you give you this guy here, right? That this approach of solving ODEs with this characteristic equation is obviously not restricted to a second order system, right? You could also here take the approach and say, okay, we're gonna solve this here via the characteristic equation, right? So the characteristic equation would here be lambda to the power of 3 plus lambda to the power of 2 plus lambda plus 1 is equal 0. Okay, so this is really a very general approach you can take here, right? Okay, so one last thing for today, and it's probably gonna take 2 minutes. Why the heck didn't we talk about PT3, PT4, PT5 system, right? This originates back to this here. This is now a PT3 system, right? It's a system with a third order, a proportional system with a third order leg. Why third order? Because it has the third derivative on the left-hand side of y. Okay, if you solve that, and I'm not going to do this because it's this polynomial of third order, but what you will get here is that lambda 1 is equal minus 1, and this here is, I think, plus minus I. Okay, these are the solutions, and now what happens is this basically is a PD1 system and this here is a PD2 system. So this is important, higher order system can be decomposed in PD1 and PD2 systems, right? And this is quite important, or this is actually quite nice, because that's why we don't need to talk about higher order systems, because we understand now PD1, we understand PD2, and we understand, okay, if I have a PD100 system, I can decompose it in a lot of PD1 and PD2 systems. How do they come together? Well, the answers, when you look at the time response, they are just adding up, right? So they are just added at the output. So all we need is PD1, PD2. Okay, that's it. In the afternoon, we're going to do integrating system and differentiating system, and we're going to close the time domain view on system dynamics to we'll be able to move into the Laplace domain next week. Okay, hope that kind of was illustrative. I know PT2 system usually takes a lot of time, but this is really a basic system we need to understand. If we understand that, every other thing comes kind of handy or easy because it's similar. The only last part we need to understand in the afternoon is what does it mean when we had an integrating or differentiating system. If it's proportional, integrating, or differentiating, only concerns the right-hand side of the ODE. This is one thing you should think about it in the next 2 hours. It's only important how our input is transferred to the output. So if it's proportional, integrating, or differentiating, or any combination of it, what we will see can be, will just come up from the right-hand side of our ODE. Stay safe and see you later. Bye-bye.